Hey guys, mm, I'm making this short video for you guys to introduce you lab 5 on friction. Today you are going to explore about the friction. You'll use online simulation to determine whether the acceleration of an object moving downhill depends upon angle of inclination of a plane it is moving on when the friction exists. Okay. What else? Then you will compare the acceleration for uphill and downhill motion of a car that's sliding along the plane. Next, you are also going to build your own experimental setup with materials available at your home. We'll talk about that in a bit, in few minutes. So let's say resources and equipment. You'll need a simulation from O physics. You'll need ruler. You'll need 3 objects of your choices for building your own setup. So for example, like calculator, phone, ball, or something like very tiny notebook or something that will be needed later on for part 2. You'll also need something like a chopping board, or maybe cardboard, piece of cardboard, or something that you can make inclined plane. Okay, or real inclined plane means really like you can form a ramp. Okay. So part 1, there are several equations, useful equations here. If you look at I'll try to write a little bit bigger. I'm not sure how, if you guys can see from there. Let us see. Fs max equal to mu s, and this here is Fs max means maximum static frictional force. Okay, mu s is coefficient of static friction, n is normal force. This guy here, this mu Sn, called coefficient of static friction. You can also find this quantity by this mu is equal to tan theta max. This will be clear as we talk about the setup in later part in this part 1. Okay, so mu s is 10 theta max. This theta max is the maximum angle. We'll see that what does that mean in few minutes. Fk equal to mu k n. So kinetic frictional force equal to coefficient of kinetic friction mu k times n normal force. Do you see this is, let's call this guy equation 1, let's call this 2, let us call this 3. If you like it, you can call Harry, Jack, I don't know, Sam or something like that. Okay, just we're just writing this number so we can call it later easily. So now, do you see similarities between these 2 equations here? This has a coefficient of kinetic friction, this has a coefficient of static friction. Both of these quantity, this thing has to do with the surfaces in contact. Now n is normal force. It turns out to be mz cos theta. Okay, for an object moving along incline at an angle theta. Now these are the equations. You already have these on your handout, so I'm going to just erase it. But what I'm going to do is kind of try to make some figure that would be helpful for you. So let's draw a free body diagram of an object of mass m moving downhill along a plane inclined at an angle theta. Assume friction exists between the mass and the incline. So let's say almost. So let's say this is angle theta. Let's say we have some object here this has mass. It has mass m. Okay, now this object is sliding, so there is a friction between the surface here. And this object is sliding downhill. Let us call, for simplicity, let us make this side as our x. Okay, just for us, so it is easy. Let's make this as our, oops, I want to make that perpendicular to x-axis. Just call this as y. Okay, okay, so this is we have this object, okay, moving, it is moving along the inclined plane. Now this ramp is at angle, inclined at angle theta. Now we said friction exists, so let's look at a few things here. If it is sliding along downhill, then this is moving this way, right? Now the moment we bring any kind of matter or any object, any mass, this will have some sort of weight, which is due to gravitational force. So let us write that down here. In this case, let's say it's pointing downward here, okay, W. Now because these two surfaces are also in contact, this object is on inclined plane, there is also normal force pointing this way. So that's from the surface here, okay, I'm not showing it here, so maybe you could really imagine that this is coming all the way from down here, so going up, okay, really like this is probably the better way to say it. Okay, so there is also normal force. Okay, now if this object is going downhill, important thing is what should be the direction of the frictional force. If it is already in motion now, then it must have a there must be kinetic frictional force here. Okay, so the friction always acts in a direction opposite to the motion of an object, which means if this object is going this way downward, then the friction, let's say Fk, must be acting this way. Okay, so this line is parallel to the surface. Okay, all right, so now let's look at the total force. So what we could do is really, we could kind of, use the geometry here, and then if we do the geometry, like resolve this vector W here, it turns out that this is going to be, oops, this is going to be like, sorry, this did not write. Okay, so if we resolve this vector, then we'll have something like this. So resolve this vector W into two components, then we are going to get something like this. So it turns out that from geometry, this angle also turns out to be theta, so this becomes W cos theta, this becomes W sine theta. Okay, now this component here must be equal to this guy here, so which is in y direction, and then these two, W sine theta, and then Fk, they are working along x direction. Okay, so now if this object is moving this way, so let's look at this. It is not moving, so let's look at the in two different directions. Along x direction, we have a total force. If we apply Newton's second law of motion, then the sum of the force must be equal to what? Sum of the force must be equal to this force, right? What do we have here? If we consider this W sine theta as a positive side, then we have W x minus Fk, right? You see, I am writing this minus sign because these two things are Fk and W sine theta are, pointing in opposite direction, and we assume our x-axis is positive downward. Okay, now this total sum of the force is nothing but this is m times a, which must be equal to Wx is what? W sine theta. In W is really m times g, so I'm just going to write mg sine theta minus Fk, I just told you a few minutes ago, Fk is what? Mu k times normal force, and n is what? This n must be equal to W cos theta, so I'm just going to write that W cos theta, cos theta. Okay, this part, if you guys don't understand this, this is what? This is n, oops, this is mu k, n, and then mu k is what? N is just m times z cos theta, okay? Really that. This normal force is equal to W cos theta, so I'm gonna just erase this W, okay? So really just write that quantity here. Mu k mz cos theta. Now you see there is this m here, there is this m, there is this m, so I'm mentally just taking them common. If I take this out here, if I take this out here, then I can cancel those, so I'm not going to write them. So the acceleration is just what? Z sine theta minus mu k times, really there is also another z here, so really I can just say mu k cos theta. Okay, so this is the acceleration of an object sliding downhill when there is the friction between these surfaces in contact, these two surfaces in contact. All right, so this here important. Now if you want to make a free body diagram here, we could just do this, right? So let's say we could just say, like, you know, object is going this way, right? So that's the acceleration going that way, and the net force really would be, and then there is also like normal force, and then, oh really I don't have to really make it, let me make it before the resolution. Let's do, so the object can be represented as dot, and then let's say that the weight is W here, and then normal force is kind of going like this, and then Fk is like here. Okay, oops. Okay, so now what shall we do? Let's look at number 3. So in part 1, number 3, oh actually before we do that I wanna say one more thing. So okay, this is for downhill, right? Let me write this down. Let's do, if we had an object that's going uphill, how does this changes? Uphill. So instead of this guy going this way, we will have object now going uphill. So I'm gonna erase everything. Maybe I'll just remake, okay? Remake this. I'll leave this equation for you guys there for me. So for uphill, downhill, let me write up here. Uphill. Okay, here is an object. Now this object, it has a mass, it must have a weight here pointing this way. If these surfaces are in contact, there must be normal force acting perpendicular to the surface, so this is the normal force. And then if this object is now going this way, this is moving that way, okay, velocity, and then because the friction always acts in the direction opposite of the motion of an object, so the frictional, kinetic frictional force must be acting along this side, Fk here. So now again, let's do this. Let's call this as our positive x-axis, and then the other this as positive y. So downward is positive, okay, for now also. Now let us see. Again, you can use the same thing, like you can resolve this vector w into two components. So if you do that, then you get here what, like w cos theta, and then you will have w sine theta along this way, along the x-axis, and rest are same. So which means along, so let's look at, I guess earlier I did not tell you guys about along y-axis. So along y, what happens is, along y, really n equal to total force, sum of the total force equal to what, n minus w cos theta, but the object is not accelerating, so we have a 0 this side, so n minus w cos theta. And then if you write one more step here, then you get n equal to w cos theta. This is how we get that n equal to w cos theta. Okay, now this is the along x-axis. This was, we initially wrote this for downhill motion. Now for uphill motion, the only thing, look at this, the thing that's going to change is, this is Newton's second law, right? Total sum of the force is equal to whatever we have here. Total sum of the force equal to ma, but you know, total sum of the force here we have is what, wx. Okay, along the x-axis we also have kinetic frictional force, but now both of those, the x component of weight wx and the kinetic frictional force, are in the same direction, meaning they must add. It's like, okay, so they are in the same direction, so this sign is positive, rest are ditto, nothing changes. Now this is just positive, I'm just gonna make this as positive. Okay, so now you see for uphill motion, acceleration is now bigger. Why? Earlier we had negative sign here. So let's say you are given 30-degree angle, value of g is constant, sine 30 minus this mu k is also constant for the given surfaces in contact, and then cos 30-degree, right? So if you had a minus sign here, this whole thing is going to be a smaller value for downhill motion. But for uphill motion, actually they're adding up, so this whole value is going to get bigger. So acceleration is actually, acceleration uphill is greater than acceleration downhill. Okay, so now you see why acceleration uphill is greater than downhill. So both the gravity and the gravitational force, which is really the weight here, right? Gravitational force as well as the frictional force, they are trying to slow down the object. That's why we have now, there is a higher acceleration going uphill in comparison to downhill. Okay, that is the important part. Let us see. So you guys, you are given in your handouts really like this part of the equation, but then to actually do your lab, you kind of have to do this part here. Okay, this will be needed for theoretical calculation of value. So theoretical calculation of acceleration has to come from here. So you will have everything from simulation. You know, g is 9.8 meter per second square, and then the theta is your choice, whatever the value you want to choose. Mu k is also given in the simulation, and theta is again your choice. Okay, so you should be able to get those values there. All right. Okay. There is this interesting question. So, okay, predict whether the static frictional force is greater than the kinetic frictional force. Choose one angle and based on the data given in simulation, verify your prediction. So this is in number 5. So I'm going to erase this, okay? Here, so we saw equation, right? For Fs max, we have mu s n, which is really mu s mg cos theta, right? Now you guys know why n is mg cos theta is max, right? Okay, so this is let's say the equation 1. This is equation for finding maximum static frictional force. For kinetic frictional force, Fk equal to mu k times n, which is really mg cos theta. Okay, so this is 2. If you really look at these two equations, let's say for if you are to use simulation, you are pretty much given everything. You are given this value, you are given this value, you are given this, you are given this. You are really, you can choose the theta of your choice. This is same, so this guy and this guy are the only different. These two things, m times z, this m times z, they are ditto, same number, right? If this is 2, this is also 2. Here this part is also same. If you choose the angle, one specific angle, this part is also same. So these two are equal, these two are equal. The only thing that's gonna matter is really depending upon if this value is bigger than this value, then this whole thing, static frictional force should be, maximum static frictional force should be greater. Okay, so that's the way to just compare whether the static frictional force should be greater than the kinetic frictional force. So for number 5, you really have to do just calculation, really nothing else to do. Like, you don't have to do any simulation, really just look at on the simulation, plug in the value for these things here, and then just find the value of this and this guy here. Okay, for number 7, for determining the coefficient of static friction between the surfaces. So this is where you have to build your own ramp. So again, use chopping board or part of the cardboard box or a thin books, etc. Tilt the object. Okay, so let's say if I had a cardboard box here, or maybe not cardboard, I got here my notebook here, then I would kind of put this something like this, maybe like like this on the surface. I don't know if you can see, but if this is like this, so put it here and then maybe put something here on the side, so you should be able to see. Then it is gonna be just gonna look like that ramp, should look like ramp. And then you have theta here, you should see this as 90 degree. You should be able to calculate what this theta is, right? Now that's why you need a ruler here, because you have to make a measurement of the sides here. So sides here to find the theta. Okay, so use the trigonometry, find this angle theta. Easiest way to do is what you could measure any side really, but tan theta is probably better there, because you will be using tan theta for this part. Now for this part, these important things to look at is this, the tangent. So the coefficient of static friction between the surfaces can be found by finding this angle theta. So let's say I had this as a ramp. Now this ramp, I was tilting it, and then let's say I had this as my object here. So let's say this is, imagine there is imaginary surface here, okay, down here, and then I was tilting it, see. So you have to make a measurement of each of these angles. So you start from like a small angle, see, okay, it doesn't decrease, it's not moving, see, it is not moving, see, it is not moving, see, it's not moving, right here, almost, okay, almost, oh yeah, right there. So that maximum angle at which this object is start to slide, that value of theta, if you take the tangent of that angle theta, that will give you the coefficient of static friction between these two surfaces, this surface and surface, this surface here. Okay, so that is the mu s. All right, that is about it for this lab. And then for part 2, you can you have a research question. You could do either simulation or do something cool with your experimental setup, so it's totally up to you. Yeah, and then if you have a question, reach out to us.